everybody, and welcome to Qubit Confidential. This is a new podcast that takes a behind-the-scenes look at the quantum world. I get to ask experts to share their insight on how quantum technologies are reshaping everything from computing to cryptography and beyond. My guest today is Stephanie Simmons, Chief Quantum Officer at Photonic Inc. Welcome, Stephanie, and thanks for joining me.
Oh, thank you. Yeah, thanks for your interest. Excited to be here.
So we met in person a couple of times, but I'm delighted to be speaking to you in the context of our podcast.
Yeah, me too.
I want to ask if you could share what sparked your interest in quantum physics. What was the initial kind of trigger moment? Was there an aha moment? And then how did you end up specializing in quantum computing?
Oh, it's a great question, and it's a little bit anomalous, but I actually came at it the other way. Yeah, so I was just, serendipity plays a role in these things. I grew up in Southern Ontario, just not too far from the Institute for Quantum Computing.
Wow.
And the launch of that in 2001, when I was so young, I did hit the news. It hit the news locally in the local paper, and I just thought the concept, I was a total computer geek, and I thought the concept of quantum computing, where you could use teleportation to do things, I was just like, oh, well, this is going to be the future for sure. So I actually fell in love with that concept very early and never looked back. I mean, a lot of people in STEM find something that they fall in love with, whether or not it's be astronomy or whatever it is. Mine ended up sticking with it the whole way through. So I got a few different degrees, and actually physics wasn't one of them. I got math and computer science and then material science, and I worked in electrical engineering department.
Wow.
And then ended up being a physics professor, but it was all quantum computing.
Yeah.
All quantum computing from the ground up, right? From day one, which is great. I think we were the first generation back in the 2000s to be pure quantum computing and not from something else coming in.
No, it's fantastic. All quantum all the time.
Yeah, all quantum all the time. I mean, it's like, how can you not? Like, well, okay, let's think about human history, right? Well, this is what human history is. It's like, frankly, it's the commercialization of various branches of physics.
So,
like, when you think back to what worked 100 years ago, 200 years ago, you think about what physics they had commercialized by then, right? Electromagnetism, steam engine, and thermodynamics, nuclear, right? Like, all of that's what human history looks like. So I don't know. It's just kind of pattern matching.
So, Stephanie, I have to share with you that when I do opening remarks at these quantum events, I use your quote as one of my.
Oh, do you really?
All of human progress has been driven by physics. Here's my parent.
Oh, okay. Well, I mean, the sentiment is in line. I don't know. We do owe a lot to, let's say, most. Yeah. Well, no, but that's what human development is. We've gotten really good at that, understanding and deploying what we understand. And physics is only just one of those. They're very foundational, of course, but I wouldn't say it is unique, like in the sense like medicine and chemistry has also been like amazing in terms of human change. But quantum, oh my gosh, can't wait.
So I'm a believer. I'm a fan.
Oh, totally.
So let's move to the present. So as Chief Quantum Officer, what does your role entail? And particularly, how does it differ from, say, what a traditional CTO, even a chief scientist role might play at a company?
Yeah. And you're asking kind of, what's the difference between a chief science officer and a CTO? And then where does this fit in the middle? Because, well, they're different, right? Yeah. So if you're a science officer, you're responsible for the science of the organization. If you're a technology officer, you're responsible for the technology of it. But we're still building out, like, essentially I'm a quantum engineer, right?
Uh-huh.
And so is that science? Is that technology? It's definitely quantum.
Yeah.
Right. So if there's like an unambiguous term that kind of covers both of those, because there will be akin to like the very early days of semiconductor physics being commercialized, right? Taking a look at transistors.
Yeah.
There was still so much science that went into that technology. And the leveraging of that in directed research towards achieving better commercial outcomes, right?
Yep.
That bridge is so important, right? So it was, by design, something that covers both of them, because you can't just come at it from a science and science perspective. And if you come at it from just a tech perspective, you miss the opportunities to think about this in a 10, 20-year span where it will all change and evolve and unlock so much more than we could even see today.
Yeah, yeah. So I'm going to get into the sort of qubit landscape modality conversation with you, right? So
Yeah.
we're aware that many quantum computers today are based on, say, superconducting qubits or trapped ions.
Yeah.
There's a whole landscape of modalities that people are exploring. So I want to get your take on why Photonic is focusing on photons and defects in silicon. So what are the key technical breakthroughs that make photon-based quantum computing viable, or more viable, if you will?
It's something that it is tied to the history of it all, because I did come up through the quantum space, and all of those modalities were kind of all the other main modalities were all on offer in about 2004, 2005, which is when I came in, including things like neutral atoms. Like they started way back then.
Yeah.
Um, and I was taking a look at it and I was like, I was really honestly maybe just a bit naive, but pattern matching on what had been successful in the semiconductor industry. I was thinking, like, how do we get this so that we can rack mount and modularize what we have and deliver fields of quantum,
Right. Well,
right?
leverage
How do we,
technology, right? You'd said, I think, leverage
sorry, say again?
the heritage, the legacy work in that space. So anyway,
Yeah, well,
interrupt you.
yeah, and it's really working backwards from that picture of limitless quantum. What does limitless quantum actually look like? It means, in a practical sense, it's probably going to be connected by telecom photons eventually.
Yeah.
If you take a look at that, like in a second order detail, the link into those telecom photons has to be exceptional, right? But really, it's about thinking about costs and deployment speed. Like, how do we get to market and meet customer needs quickly? If you take a look at all of the hard proofs in terms of resources that are needed to unlock customer applications in quantum, which is when this whole thing becomes a real party, right?
Right.
You need something north of probably 400 or so logical qubits at what I'll call like silver grade logical qubits. They can't just be entry level logical qubits. They have to hit a certain performance.
Yeah.
So if you're working backwards from that, it doesn't seem to be that there's many approaches that could fit all of that kind of resource into one box. And so I had it's just an axiom. Lots of people have different axioms, but our axiom was, hey, let's take the assumption that a distributed architecture wins or will win in the limiting case. Because I'm in it for the long run, right? Like I was in it for 40 years. I'm like, I'm going to be here. This is a career that's coming. This is inevitable. The question is when.
Yeah.
Right? Because we know the value this produces, right? So if you work backwards from that, you have to have two things in mind. One, you have to have the photonic interconnect. It's so important. That is the name of the company. But the photonic link so that it can do entanglement distribution. It's a detail, but it's a super important detail.
Yeah.
But you also have to have lots of qubits into any one box. And so the way that we're thinking about it inside Photonic is to think about scale up and scale out. So scale up is how many qubits you could put in any one box. They all need boxes. They all need to be super high performance controlled systems.
Yeah.
And then how many you can link together. And what we're really excited about the technology that we have is we can hit the upper echelons of on-chip in-box density as well as scalability, horizontal scalability, scaling out, having lots of different modules working together. So it is like scale will win this. This is how we deliver customer value. Scale, performance, speed. So yeah, that's how we're thinking about it.
Cool. So I want to get into the weeds a little bit with you. Again, a topic that's top of mind in the quantum community, which is the challenge of quantum error correction and fault tolerance. So how does the photonic solution address that, seminal problem, if you will?
So yes, this is so important. When you're taking a look at working backwards from customer value, right, where you need these 400 or plus logical qubits, silver grade, then you take the assumption that it's going to be in a distributed system. That means that probably you can design your connectivity however way you want, right? You can take photons and put them anywhere you want via fiber and switches, right?
Right.
So there is this belief, and so strong, this belief in the field that the only way you could do quantum operations the only feasible way you could do quantum operations was through proximity, right? Just smushing qubits on top of one another, metaphorically.
Yeah.
But not so different. This, I mean, really, that is in some cases exactly what they do. And this has a very strong limitation in terms of what you can do for error correction. Super strong. It forces you into like one or two choices. There's some like twists on those choices, but they're all these planar codes. And this was the thing that people said, hey, you're going to need 20 million physical qubits. And there's like variations on that now. But to do anything useful, you got to get all the way out there. Physical qubits. Oh, gosh. Those overheads are crazy, right?
Yeah.
Now, right. So there's a lot of teams that are thinking about different ways of bringing down those overheads. And what we were able to do is basically meet a open question that had been posed to the field for about 10 years. So it was known that those overheads, you didn't need them so long as you could connect your qubits in a different way. So long as you're not using proximity, so long as you could allow for some non-local interactions, those overheads go from like 3,000, 5,000 down to 100 or 50 or 20. It's amazing, right? And that is far more engineerable. So again, we just went into this space saying, hey, what would be the best if we were to unlock it? Not like knowing that as a fail-safe, we could have designed for any of those other codes as well. But knowing that we had that option, we did do the work, and we're really happy to share a few weeks ago the fact that we've unlocked that for everyone now to benefit from. The entire world has been brought 20 times closer to commercial value. So we're really excited about that, because we do know how important it is to take down the intense resource costs that commercial applications would otherwise require.
Yeah. No, great. Very exciting. I want to go back to sort of the silicon conversation again, just because I think it's, people aren't totally clear on, again, how we leverage 75 odd years of sort of foundry technology, right? So what's your take on the advantages of using silicon for quantum computing, and how does it integrate with existing semiconductor technology?
Yeah, it's a great question. I mean, it's so important to so many modalities that you'll see that most modalities now say they're kind of silicon based one way or the other, right? It's kind of interesting because you do make use of nanofabrication for many of the systems out there. Even the vacuum based systems really do use a lot of the planar manufacturing of silicon, which is great. We can understand that material. The reason why I think it's important is what we need for the scale up and scale out solution is we need to make sure we have objects in the silicon that can route the light. And this gets into a bit of a detail, but that light is the glue that holds the whole quantum supercomputer together. And so if you have like a vacuum-based system where you're only clicking into the silicon, it's not as effective as just having it baked right into the silicon itself. So the solid state of these defects is also, from a quantum perspective, outstanding, right? So it was known 20 years ago that the quantum performance of quantum bits in silicon are just amazing, right? Lots of nines, 3-hour coherence times. I was fortunate to participate in that work about a decade ago. I mean, these things are just gorgeous, right? Gorgeous qubits because they're so simple.
Yeah.
Right? There's nothing exotic. They're basically like trapped atoms, and you get all the kinds of capabilities that you would expect from a trapped atom, but it's baked into a solid crystal lattice that never moves and doesn't have noise around it because silicon's so clean. Right? So it not just works from an economics perspective, and from a practicality and a manufacturing perspective, but it does work from a quantum perspective. So like ding, 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 let's get the solution working, right?
Yeah. So I have to ask you, since I'm, conversing with an expert here, I have to mention that the CEO of NVIDIA blew up the internet recently with his proclamation that we're, 10 to 20 years away from viable quantum computing. Then Bill Gates weighed in, kind of a few weeks later, saying, well, it could be sooner. I forgot what his number was, 3 to 5 years maybe. But anyway, from where you sit, how far are we from seeing widespread commercial applications, and in this case, of photonics, quantum computing technology?
Yeah, I'm happy to answer that. And I'm not even able to answer not just from us, but from others. So what these QLDPC results where we did move the goalposts in 20 times, it is true that the NVIDIA team didn't know about it when they made those announcements. And it is the case that they have a really highly capable team in-house that I think believe those different numbers.
Yeah. Assume.
So there's also, and it's really interesting, the US government also believes in that kind of 5-year horizon. through what they're calling the DARPA QBI program. So I'm not sure if we've spoken about that before, but you're familiar with it, I'm sure, this QBI program.
Explain what that is for our viewers.
Yeah, absolutely. So I'm a huge fan of this program. I think it's just brilliant. So the program that the it's a US DARPA program called the QBI program. And it's based off a pilot program that Microsoft and SciQuantum and a few others had gone through, started 2 years ago. But this new version is now opened up to all international quantum companies scale. So the QBI program, it's bounded to 8 years. But most of the teams have at least, I think it's fair to say, most are aiming for something a little bit sooner than that, because there is, such an opportunity here. And there's so much advancement happening all over the place. And we do know that these are like mathematical proof of product market fit for the kinds of applications they're looking at. It's not the speculative NISQ phase of quantum all over again. This is working backwards from how many qubits are needed, how much will it cost to deliver something useful to a customer. It's brilliant.
Yeah.
And so if the company goes through this program, through this intense diligence, there's 3 stages. Stage C actually accelerates the team. So whoever gets through will be able to tap into $300 million per company in matching funds to accelerate their work, right? So this is the act of conducting the race. And I'm a big fan of this program because it really is just focusing on delivering what's necessary, right? It's cutting through all the noise, all the marketing flags, and all the rest of it. What is the serious job of doing the work to deliver customer value?
Yeah.
Right? It's great.
Oh, that's great. So I'll put, by the way, viewers, I'll put a link to this information about the program in the comments when we post this. So just FYI. There's a lot of focus on sort of vertical specific solutions in the quantum computing space, right? Companies that are focused on financial services or on drug development, drug discovery, material science. Wonder what your take is. Are there specific industries that Photonic thinks will benefit near term from your approach? Or
absolutely. I think there's a really healthy conversation. Again, looping back to this DARPA program, you do need to design for specific applications for these things. Now, having said that, all of the offerings out there that we're aware of are targeting a utility scale universal quantum system.
Right.
And that means that in principle, they could apply any one of these algorithms, right? It is the case that there are unknowns in the realm of heuristics, right? So there's deterministic algorithms, and including that is all the different algorithms to do with chemistry and material science and all the rest of those. Those are deterministic algorithms. We know how many qubits we need, how long that needs to run to deliver value, and that can feed into different programs, and that has widespread applications. The other one is, of course, Shor's algorithm and having something that's a cryptographically relevant quantum system. Same kind of scales, right? We have to think about this as a set. But I'm also really keen because once we start unlocking some of those pieces, there will be a world of exploration around the heuristics that we don't yet have a good handle on. And we can't almost by definition, because these heuristics just tend to work, right? And so a lot of other industries do open up in potential as we're able to have reliable quantum systems at a sufficient scale to test out heuristics in all of these different places. So the story isn't finished. And I think actually I'd link back to the start of this conversation. When we first started to commercialize semiconductor physics, they already had computers, right? They had like the code-breaking computers in World War II, right?
Enigma.
What they had excitement about using semiconductors and transistors was hearing aids. Right? They weren't thinking like Facebook or AI, right? They were thinking, or the internet, they were thinking about hearing aids. So there is this trajectory that typically runs its course as various, like when people were thinking about the steam engine, they weren't necessarily thinking about heat pumps either. Like these things tend to build upon each other as really strong infrastructure pieces that get leveraged in ways that the inventors almost never expect, right? So I'm excited for that phase. We'll see how that goes.
No, me too. Let's talk about partnerships and business relationships. So can you share some insight into, who Photonic is working with to accelerate quantum adoption? Are there other companies? Are there partners? maybe in specific verticals, or just curious to know, what kind of relationships you developed to move the business
Yeah.
forward.
Yeah. So we, again, very new modality, right? So we've had a situation, we invented it. I went and looked for this as a professor 10 years ago. We found the T center, which is the color center in silicon that can unlock this distributed quantum computing thing in a solid state media.
Wow.
That we found, and we only shared that with the world, its invention or reinvention in 2020. So things are moving really quick, but that means that there was a lot of full stack work that we had to do because a lot of the assumptions that people had based upon other modalities didn't like click in through the stack, including, for example, assumptions on error correction or on what's needed for really any of the controls or the rest of it. So that's changing now. So we're really excited to have more and more of those kind of like supply side partnerships, and we do have a few of those. But let's talk more about the customer side.
Yeah.
We had a great interaction a few years ago. We kicked off. We shared with Microsoft what we were up to. We were stealth for many years, right?
Yeah.
Because we knew the value of what we had going on, and so one of the things we did early was we shared with Microsoft, like, hey, like maybe this is a thing you might want to be paying attention to, in a kind of a collaboration sense. And because they've become famous at collaborating with, disruptive other firms, and that's like one of their business models going forward. So we really like that. It's working really well for us. So we're great fans of theirs. In some sense, we're the scale out and up kind of approach, which complements their scale up approach in-house. But really, they are a platform player. And so we're working and learning a lot together on that. So that's a great relationship that is making things go faster. We also have a relationship with a telecom provider. So one of the things that you get when you're talking about a distributed quantum computer, what you're setting up are essentially nodes of logical qubits that can talk directly to telecom light. And this is not, that kind of means that the network is the solution for scaling quantum computing, but also that computing is the solution for scaling quantum networks, because that node is the same thing from a technology perspective as a repeater, which is the thing that everybody's been looking for to unlock quantum networks. So we do have a great relationship with TELUS. And so that kicked off a little while ago, and we're using metropolitan deployment. We also have customers, but we're not doing broad availability of our technology. We have very selective partners that we work with for test and evaluation and feedback. So that's working really well.
Well, thank you for sharing that. I want to get your take on another topic around sort of interoperability between, say, quantum computing and classical. And we're seeing people talk about, putting quantum computing solutions in HPC settings, if you will, or in data centers, server farms, or whatever. Just, want to get your take on how that interoperability will develop and evolve and deliver value.
I think it's a great point. And in some sense, it's one of the things to look at when determining when commercial value could click in, because there are questions that could be answered by quantum computers and like kind of an element-wise basis that could be fed into a far more deployable, let's say, AI system, right? And so that could have mass deployment without giving access to something that could alternatively be used to crack cryptography, right? So there's a really good relationship with those kinds of interactions. I think it's actually the combination of these things are going to really unlock the most. HPC, of course, helps quantum because there's going to be a lot of really helpful runtime calculations and compiling and the rest of it that make it all sing. Absolutely. But there might be ways of folding that back in and offering better material design for some of the challenging engineering problems faced by the next generation. So there's the combination of all of these things are going to be really lovely to watch. And in some sense, we're going to want to have things co-located, especially if we start thinking about quantum networks as an ultimate layer of information communication security. In addition to PQC, right? PQC, post-quantum cryptography, we got to do it. Everybody has to update their cryptography. Like if DARPA and all of these teams believe that a cryptographically relevant quantum computer is like 8 years or so, we should really, we should really think about post-quantum. But then we should also think about within data centers deploying on-site quantum resources to allow for information transfer in provable physical security, in the sense that you can prove that it hadn't been eavesdropped. That's great. As an ultimate layer of security, right? So there's going to be a lot of ways that these things build upon each other.
That's great. So let's fast forward 10 to 20 years. Look in your crystal ball, wax philosophic, whatever. What do you hope Photonic Inc. will have achieved? And even what will you be doing in, say, 10 to 20 years?
I think that's when it's before then, but that's when there's a real market and real opportunities coming up thick and fast. I think it'll be akin to the way AI is thought about now.
Yeah.
Where they kind of had that germination phase and then they had their big moment. And so it's going to be a thriving industry. I'm really excited. It's great. It is really all moving very well.
Yeah. Speaking of a thriving industry, good segue. As you know, I'm a fan of talent development and workforce conversations. So I wanted to ask you for your advice, maybe for young scientists and engineers, but also other talented people who are interested in science and bleeding edge technology, who might be interested in getting into the quantum field. How would you advise them?
I would say go for it. It is inevitable.
Yeah.
So that's great for careers perspective. The way that technologies tend to sort through is that there tends to be a consolidation phase where talent is scarce and everybody is very sought after. And so that's great for employment, right? Yeah. So that's a good phase to go through, and that's coming up. So now's a good time to get in.
Yeah.
I would share that there's actually lots of subject matter specific humans that can contribute to quantum. You don't need to be a physicist. We have, here at Photonic, only say about a quarter, maybe a third of our R&D team have quantum. Actually, you need a lot of software. You need a lot of hardware development, right? You need a lot of manufacturing. So there's pieces that don't require one's understanding of a Hamiltonian to be successful.
Yeah.
But I would share that one of the things that I've noticed in this 0 to 1, as we're really all just building out the first commercial viable product, not flag waving vanity metric offerings, right? A real commercial product, which is just harder than what people have been doing so far, but that's where everybody's now moving, which is great. In that phase of the evolution of this technology, you need what I would call Venn diagram humans. Mm-hmm. So the more that you can speak more than one language, either business and software or management and manufacturing, or whatever the combination is, you just end up having such a disproportionate value in having people speak multiple languages around you and just glue it all together. So you're actually making the most of everyone. And so the more you can do that as you come up through your career, I think the more value you can provide. And that can be, those are very broadly deployable skills, right? If you have that kind of Venn diagram capability, you end up you're more unique and then more valuable.
Yeah. Oh, that's terrific. I love that metaphor, that image of, a multiplicity of sort of capabilities and skills that you bring to an opportunity.
Yeah. And you bring different problem solving techniques, the more lenses you bring to the table, right? So it ends up having quite a nonlinear benefit.
Yeah.
It's really helpful.
That's great insight. So, Stephanie, we're excited that you're going to be joining us at Quantum Tech USA. I'm looking forward to seeing you again in person.
It'll be fun.
In Washington, D.C. in April. Can you just share with our viewers your take on the value of in-person events like Quantum Tech and how they help drive the quantum agenda forward?
Yeah, and it's a great question. And I'll link into kind of the topic we just shared. So the more you can bring kind of serendipity into these conversations during this 0 to 1 phase, the more kind of combinatorial gains you can get. And you don't get that from just a webinar, as it were. If you're just getting one information dump, you can get value from that for sure, but you don't see the full spectrum of the kind of sidebar conversations that get sparked up in different ways of opportunities that are just not evident in the kind of direct downstream kind of interactions. So I really do benefit from, just seeing more patterns and do pattern matching and meeting with humans that otherwise would be too timid to reach out, or otherwise, right? Or the other way, right? So it's, yeah, no, I do think it's good to carve out time for these kinds of things, just to see that constant evolution and map, and then build upon it together, right? Coming together. It has a really helpful effect.
Yeah. Well, we're excited that you're gonna join us. We've come to the end. I want to thank you, Stephanie, for joining me today. I really enjoyed our conversation.
Thank you so much. Thanks for having me.
Yeah.
Really appreciate it.
So I want to invite viewers to follow you and Photonic on LinkedIn. Check out the website. It's photonic.com. They have a terrific blog, by the way, and you can also sign up for email updates there. They post to X/Twitter with the handle at Team Photonic, so you can follow them there. I would also invite you to subscribe to Cubic Confidential so you don't miss any episodes. And you can follow Quantum Tech on LinkedIn and X, formerly Twitter, to keep up with our latest content and activities. And again, mark your calendars. Join us at Quantum Tech USA in Washington, D.C., April 14 through 16. Thanks to all of you for watching, and we'll see you in the next session.